morning everyone. So here is my second lecture based on optical communication. The topic is basically cylindrical modes, fiber types and its parameters. So in the previous lecture we have discussed about the planar waveguide modes, the basic ray theory, analysis of the optical fibers, and in this lecture we are going to deal with cylindrical structure of the fiber, and the modes which are transmitting in the fiber is cylindrical modes. So here what is cylindrical modes we discuss first. So basically cylindrical mode, the cylindrical waveguide however is bounded in two dimension as compared to if you compare the planar waveguides, it has only one dimension, but in cylindrical waveguide it has two dimension and it is represented with L and M integers, and these integers are basically necessary to function as the modes traveling inside the fiber. So we will see how the planar waveguide is different from cylindrical modes, and apart from the planar waveguides, whatever there are modes, that is TE, TM, here we have different type of modes. So for cylindrical waveguide, we therefore refer to TE, LM and TM, LM modes. So it is TE, LM and TM, LM modes. So these modes corresponding to meridional rays, which we have already discussed that what are meridional and skew rays. Those rays which are passing straight through the fiber axis are called as meridional rays, but those who are follow the helical path are called as skew rays. So in cylindrical modes as well as in planar waveguides, we use basically meridional rays which are traveling within the fiber. However, hybrid modes where Ez and Hz are non-zero also occur within the cylindrical waveguide. So if you remember, there are transverse electric and transverse magnetic modes in the planar waveguides. So transverse magnetic and transverse electric modes, how we define that? We define the transverse direction and the direction of the propagation. So we define here the direction of propagation Z and the transverse direction X. So whenever the electric field is in X direction, it is called as transverse electric, and in that direction the magnetic component is 0. So the magnetic component will be in the direction of the propagation of wave, that is Z direction. Similarly, if we have magnetic component in the direction of the X, it is called as transverse magnetic, and in that direction the electric component is 0, and in that case the electric component is in the direction of the Z. So we have their transverse electric and transverse magnetic modes. So here the similar thing is here also, that is in cylindrical modes, but here the number of modes are 4 here, and these are called as HE and EH mode. Apart from TE and TM modes, we have two different modes here also, that is HE LM and EH LM. So if the component H is at the initial and the electric field at the next to H, then it is called as dominating thing is here magnetic field, and in the second one we have electric component is at the first and the magnetic component at the second place. So we have the dominating component, that is electric field. So we have here HE and EH depending upon whether the component of H and E are making larger contribution to the transverse field. So if the contribution of electric field is in the transverse direction, then it is called as EH LM, and if the magnetic field is in the transverse direction, then it is called as HE LM. So apart from these two modes, TE, TM, we have EH and HE modes also present in the cylindrical waveguides. So here we follow the weakly guided approximation, where it is said that delta is very much less than 1 for a small grazing angle theta, and for weakly guiding structures, we with dominant forward propagation mode theory gives dominant transverse field components. Hence, approximate solution for the full set of HE, EH and TE, TM modes may be given by two linearly polarized modes. So here there is a new word come, that is linearly polarized, which is called as LP components. So these linearly polarized modes are not exact modes, because we have exact modes which are called as HE, EH or TE or TM. So these are not exact modes. These are basically combination of the set of these exact modes, which is HE, EH and TE, TM. So linearly polarized modes will be defined as something like LP01, LP11. So this is the lowest order mode, which is LP01 mode. So there is a cutoff frequency for LP11 mode, which is VC, is defined as VC, cutoff frequency or the normalized frequency, and its value is equivalent to 2.405. So below 2.405, the only one mode exists in a cylindrical waveguide, which is LP01, but above 2.405 we have another components or another modes which will exist in the cylindrical waveguides, which is LP11, LP21 and so on. So weakly guiding fiber relative refractive index is very small. Here HE and EH mode pairs occurs, which have almost identical propagation vectors, and these are called as degenerate modes because EH and HE are present in pairs also. So the superposition of these degenerating modes characterized by a common propagation constant correspond to a particularly LP modes regardless of their HE, EH or TE or TM field configuration. So we can easily summarize this as the component of E is in the transverse direction. It is electric field is the dominating thing, and if the magnetic field is in the transverse direction, then magnetic field is in the dominant thing here in these four modes. So we can have this linear combination of degenerate modes obtained from the exact solution produces a useful simplification in the analysis of weakly guided fibers. What are weakly guided fibers? Weakly guided fibers are those fibers in which the light which is propagating inside the core is not only propagating inside the core, it has some perturbation in the cladding also, or it has some component in the cladding also. So the light is not completely in the core, but it has some waves propagating in the cladding also. These are called weakly guided fibers. So the relationship between the traditional HE, EH and TE, TM mode designation and the LP modes, which is linearly polarized modes. So HE, EH and TE, TM are called exact modes and LP modes are linearly polarized modes. The relationship is given with a table here. So we can see with the table here that LP01 consists of only one mode, which is HE11. LP11 consists of three modes, which is HE21, TE01 and TM01. Similarly, LP21 consists of two modes, HE31, EH31. Similarly, LP02 consists of only one mode. So we can see that the linearly polarized mode is a set of is constituted as a set of the some exact modes. It may be a one exact mode in the LP modes, or it may be a combination of one or more than one exact modes which is in the linearly polarized modes. So how the intensity profiles are given for these modes? So these intensity profiles are obviously the electric field intensity profiles. So electric field configuration for three lowest LP modes in terms of their constituent. Exact modes are LP mode designation, exact mode designation, electric field distribution of the exact modes, then intensity distribution of EX for exact modes, indicating the electric field intensity profile for the corresponding LP mode. So it may be observed from the field configuration of the exact modes that the field strength in the transverse direction, whether it will be EX or EY, is identical for the modes which belong to the same LP modes. So you can see from the bottom figure that the intensity profile for the EH or EH modes in the direction of X or in the direction of the Y. So we have EX direction and EY direction for the electric field intensity profile, and both the profiles are similar to each other. Now we can see here with this how the electric field intensity will be for different linearly polarized modes. Suppose we are having LP01 mode, which consists of only one mode, that is HE11 exact modes, and it has shown with a circle. So it has a bright spot inside the circle. Then LP11 we have TE01, TM01, HE21. So we have some configuration of the electric field, and it has two configuration, whether it can be in X direction, whether it can be a Y direction. So this is particularly your Y direction. This is particularly your Y direction. This is particularly your X direction. So it can be in Y direction or it can be in X direction. Similarly, for LP21 modes, we have four flower type of structure, that is because of this HE or EH13 or 31 mode, and it constitute of flower type of structure, one bright, one dark, one bright, one dark spot is shown in the picture here. So these are all intensity profile, electric field intensity profile for these different linearly polarized mode, whether it can be LP01, LP11, LP21, etc. So you can see the Bessel's function variation here for L is equivalent to 0, 1, 2, 3. For J0, the value of the, obviously the J0 value at value 0 is maximum as compared to J1, J2, J3 and J4. J0 will be maximum and then J1 will be decreasing as compared to J0, then J2 will be again decreasing as compared to J1, then J3 will be lesser as compared to J2, and so on. So these are called modified Bessel's functions, and the next graph is shown for the modified Bessel's function. The first graph is for Bessel's function, the next graph for the modified Bessel function, which is represented here by K. So first graph is JLR represented versus R. The second graph is represented as KLR versus R. So here the modified Bessel's function also decaying as you increase the radial distance away from the core. So here we can see the Bessel's function solution. The electric field is given by this formula, that is ER is equivalent to J of J1 UR and G J1 of U for R less than 1, that is inside the core, and for R greater than 1, that is inside the cladding. So we have K1 omega R divided by K2 omega, and then G is amplitude coefficient here, and R1 is equivalent to R by A, which is radial normalized radial coordinate, and U and W are called the eigenvalues in the core and cladding respectively. U radial phase parameter or radial propagation constant, and W is the cladding parameter. So we have a approximate equation for U and W, which is given here in the bottom line, that is U is equivalent to A in the bracket n square k square minus beta square, and W is equivalent to A beta square minus n square k square. Here n is represented as n1, and in the next part W is n is represented as n2. So obviously n is greater than beta, so we have a condition here, that is beta should be greater than equivalent to n2 and less than equivalent to n1. So we have this condition. According to this condition only we have get these solutions of U and W. So we can calculate with the help of U and W the normalized frequency, which is V is equivalent to U square plus W square and under root of U square plus W square, and with this formula you can get K into A N1 square minus N2 square. Here it can be N1 square minus N2 square. You can write it like this, N1 square and N2 square. So this is called as V number here. So V number is normalized frequency. V is expressed in terms of numerical aperture here. Normalized frequency for fiber is basically your cutoff frequency for the fiber. Whenever the cutoff frequency is fixed, that is for V is equivalent to 2.405, the only one mode LP01 exists, and above 2.405 the other modes will exist. So V number can be defined here in terms of numerical aperture and lambda and A, that is V is equivalent to 2 pi A by lambda under root N1 square minus N2 square, where A is the fiber radius and lambda is the operating wavelength. V is also represented here as 2 pi by lambda A into NA. So normalized frequency is a dimensionless parameter and it is called as V number of the fiber. It combines a very useful manner in the information, that is the combination of V is dependent on A, lambda and numerical aperture. So as you increase the value of the core radius, the numerical V number will also increase, and if you increase the numerical aperture, the V number increases. If you decrease the wavelength, then also the V number will increase. So when you increase the V number, more number of modes will exist inside the fiber core. So it accounts for modes of fiber. How many number of modes existing in a fiber will be obviously calculated with the help of the V number. So how the allowed LP modes will exist inside the V number or in the homogeneous core waveguide. So we have seen already the Bessel's function J0, J1, J2 and J3. So we have Bessel's function and modified Bessel's function for these linearly polarized modes LP01, LP11, LP02, LP12 and so on. Similarly for the exact modes, HE modes or EH modes. Next, the value of V. So how we calculate the value of V, that is the cutoff point for various modes, that is given by V is equivalent to Vc. So Vc is equivalent to 0 for LP01 mode, Vc is equivalent to 2.405 for LP11 mode, and then Vc is equivalent to 3.83 for LP02 mode. So for numerical purpose, you have to mug up these values, that is for LP01, that is for LP11 and for LP02. So obviously at 2.405 only LP01 will exist, and above 2.405, less than 2.405 only LP01 exists, and above 2.405 and equivalent to 2.405, these both modes will exist, that is LP11 and LP02. So how we define a leaky and guided mode? So limit of mode propagation, that is beta should be greater than N2K, or beta by K is greater than N2 and less than N1. So cutoff frequency, when beta is equivalent to N2K, the mode phase velocity is equal to the velocity of light in the cladding and mode is no longer properly guided. So whenever beta is equivalent to N2K, the overall light will passes through the cladding only and there is no light propagating inside the core, and mode is said to be cut off in this case, and in that case W is equivalent to 0. And next will be the unguided or the radiation or leaky modes. When beta is less than N2K, obviously there will be leaky modes or evanescent waves. So there will be no modes exist inside the fiber and there will be only leaky modes, and W in that case is imaginary. Solution of wave equation is giving these states are called leaky modes and often behave as very lossy guided modes rather than radiation mode. So we don't have any radiation mode inside the core and we have only evanescent waves or the leaky guided modes in the cladding. For guided modes, we must have beta should be greater than equivalent to N2K. Less power is propagated in the cladding, and until at beta is equivalent to N1K, all the power is confined to the fiber core. So this range of values for beta signifies guided modes of the fiber. So we must have beta should be greater than N2K and less than N1K for the guiding of the light inside the core. So next we have a new topic which is called as mode coupling. So mode coupling is nothing but a transfer of energy from one mode to another inside between the two fibers. So when the fiber has some perturbation, some irregularities at the core cladding interface, which is shown here. So in that case, or when the fiber is bent, in that case there will be change of the power or the exchange of the power between the two modes existing inside the fiber. So waveguide perturbation means deviation of fiber axis from the straightness. We usually have a straight fiber, but we can have a bended fiber also. Variations in core diameter, there may be some variation in the core diameter. Irregularities at the core cladding interface, which is shown in the figure A. Refractive index variation, which changes the propagation characteristic of the fiber. So have the effect of coupling energy traveling in one mode to another mode, and this mixing of energy or the coupling of energy between the two modes are called as mode coupling, and obviously it affects the fiber performance here. So basically this is a kind of a loss. Obviously when the mode is transferring one power from their power to another mode, obviously there will be loss of power in between. This process also occurs. So the mode coupling affects the fiber performance also. So next we have type of fibers. We have different type of fibers. We have step index fibers. We have grid index fibers. So we can see here the index profile for the step index fibers, which is having a constant refractive index inside the core, having a diameter 2A, and the multi-mode step index fiber has a higher diameter as compared to single mode step index fiber or a mono mode step index fiber. Next we have a grid index fiber, which have a gradually decreasing refractive index from the center towards the side. So we have at the center we have higher refractive index, but when you move from the center towards the core cladding interface, we have a lesser refractive index. These are the parameters, typical dimensions for mono mode, for multi mode, and for grid index fibers. So next we have step index fibers. We can define the refractive index profile of a step index fiber with this formula, that is NR is equivalent to N1, which is R less than A. For R less than A, we have a constant refractive index of N1. For R greater than equivalent to A, which is obviously a part of the cladding, which we have a refractive index of N2. So we have two types of step index fibers. It can be a multi-mode step index fiber. It can be a single mode step index fiber. So modes in step index fibers, how we define modes in terms of normalized frequency. There is a formula written here, that is M is equivalent to V square by 2. So here we have normalized frequency, and it is V square by 2 will be the formula for calculating the number of modes inside a fiber or a guided fiber or a guided waveguide. So number of guided modes is dependent upon the physical parameters, that is A or delta. Total number of guided modes or mode volume MS for single mode fiber is related to V number, which is M is equivalent to V square by 2. So there is a question here in the example, that is a multi-mode step index fiber having core diameter is 80 micrometer, core refractive index is given here, relative refractive index difference is given here, delta is given, operating wavelength is given, and we have total number of modes if you calculate, that is around 2873. So we use formula V is equivalent to 2 pi by lambda A into N1 under root 2 delta. Firstly we calculate the value of the V, and next we calculate the number of modes, which is V square by 2. So with these two formulas, we can calculate the value of the number of guided modes which supports this fiber. Next, we have gradient index fiber. As we see that the gradient index fiber has a refractive index variation decaying type with radial distance. So we have an expression here, nr is equivalent to n1 1 minus 2 delta r by a to the power alpha to the power 1 by 2, and for r less than a, and for r greater than a, it is n1 1 minus 2 delta to the power 1 by 2, which is equivalent to n2. Here delta is relative refractive difference, alpha is here profile parameter. Note down this thing, profile parameter. Delta, obviously we know, relative refractive index profile. And so on. So we have this type of figure for gradient index fiber. Many number of modes are existing inside the fiber, and it has a gradually decaying refractive index. At the axis of the core, it has maximum refractive index, and both the sides we have a decaying refractive index inside the core and a constant refractive index inside the cladding. So we have three types of profile parameter here. First one is when alpha is equivalent to infinity, it is called as step index profile. When alpha is equivalent to 2, it is called as parabolic profile, and for alpha is equivalent to 1, it is called as triangular profile. Okay. So we have already discussed about numeric gradient index fiber NR value, and we have numerical aperture, axial numerical aperture for gradient index fiber, which is NA-R and NA0, which can be having a total number of modes, which is written here v square by 2 alpha upon alpha plus 2. So in the gradient index fiber, alpha upon alpha plus 2, v square by 2 is the number of modes. So when alpha is equivalent to triangular profile, it is 1, alpha is equivalent to parabolic, it is 2. For both these, we can calculate v square by 6 for alpha is equivalent to 1, and for alpha is equivalent to 2, it is v square by 4. So these are some design parameters, which is numerical aperture, relative refractive index difference. Numerical aperture is around 0.12 to 0.2, refractive index is greater than 1% and less than 0.4% for single mode fiber, and V number is less than 2.405 for single mode fiber and greater than equivalent to 10 for multi-mode step index fiber. The cutoff wavelength for single mode fibers are lambda is equivalent to 2 pi by lambda. So we can easily calculate V is equivalent to 2 pi by lambda C here, NA, or we can also write as 2 pi by lambda C A into N1 under root 2 delta. So from here we can calculate lambda C, that is 2 pi by VC A into N1 under root 2 delta. So these formulas we can use for the numerical purpose. So thank you so much. In the next lecture, we will discuss about the different type of losses occurring in the fiber. Thank you so much.